In the intro lecture this morning, we talked a lot about these different tools that use augmentation as a way to form representations. And I was thinking about kind of going deeper into those methods, but after kind of seeing some of the other explanation of PyTorch and whatnot, we thought that going through this notebook, which is actually not looking at unsupervised learning at all, but is just doing an example in training a supervised network. We thought that this would give people the tools to go through the later session more effectively. And so it is a bit of a departure from what I've been talking about, but the goal here is to kind of give you some insights into ways to think about training a neural network and employ different forms of regularization as well. And like, what are the things that people do in practice, and how do you kind of decipher loss curves and think about what you need to do next if you were actually faced with training a neural network from scratch. So we'll be doing it through a simple example, but then going through all these different tools for regularization. Okay, so let's go ahead and get started. So this example is built off of a simple just image classification example. And I did hear that a number of you work with calcium imaging and are kind of interested in working with image data. So this will also just kind of give you a skeleton for working with a lot of different types of imaging data sets. Okay, so what we'll do is we're going to start by working on this particular example, a very simple classification problem. So we have a binary classification, either 1 or 0 for all of our different images. And this particular example is coming from, I'm sure everyone's familiar with MNIST as like a really simple image data set. So this is similar in the sense that they're small images, kind of lightweight, easy to train, but it's coming from all these different examples in like medical imaging. So this MedMNIST data set has a lot of different types of medical imaging data. There is stuff actually now from electron microscopy that's in here, so like doing different synapse classification. So there are some neuroscience examples, but most of them are coming from either pathology or histopath or OCT or different sorts of imaging modalities for solving a number of these different classification problems. So like dermatology MNIST, right? Being able to tell the difference between different lesions. And what we'll work on today is this breast cancer data set, breast MNIST. And it's optical coherence tomography is the imaging. And basically you'll have an image and it's either benign or malignant, right? So being able to just classify whether or not there's a tumor present within the image. This is kind of a cool resource if you are working with image data, because you can easily pull all of these different data sets kind of with the same commands that we'll look at. So just something to maybe look at in the future. Okay, so yeah, in order to pull down the MedMNIST data set, we'll just be able to do a simple pip install and just pulling all of those different examples. The MedMNIST data set also, is it possible? Is yours running?
I don't know. Yeah.
So if you just download the notebook even and then just put it in your drive, then you should be able just to click on it from within the drive and open as a Colab notebook. But there is actually one thing, if someone's having problems doing this, maybe Mehdi can help, but what is it? Oh, it's like the first time you open a Colab notebook from your drive, you have to like tell it about Colaboratory. Do you know what I'm talking about?
Yeah, you can right click it. I just did this. You can right click it and then say run Colab.
Okay, so you've downloaded it, put it into your drive, and then right click to run through Colab. Yeah. Okay, cool. Oh, yeah, right. Okay, cool. So here we've just pulled in our MedMNIST data set. As you've seen in other examples, right, when we're working with PyTorch or with Python in general, we're going to import all of our packages and other things that we need that aren't already kind of embedded within our Colab. And so, yeah, so we're just kind of pulling down the relevant packages. And then here we're just specifying that we're going to work with a breast MNIST. But I guess if you wanted to work with a different data set, this kind of, you could add that in. Okay, cool. So here we're just loading in the data and then dividing it into our train, our validation, and our test sets. And we've talked about like overfitting and the idea of testing on a held out test set already. Is that? Okay, cool. So this should seem very familiar then, that we're going to have a training set. Our validation set could be used to tune hyperparameters, but still kind of considered part of our training in that regard. And then we'll test on this held out chunk of data. And I think with the MNIST, it's nice because they already have the splits in hand. So you're just telling it which split you want. And then it's always the same set of examples. You're not randomizing it. Cool. Okay. So here we're just kind of, visualizing some of the different examples in the data set. We can also get, information about the meaning of the labels. So all of the cases where we have a label of 0 is a malignant, so no tumor. Malignant, so meaning there is a tumor, and then normal and benign is labeled with 1. So as I said, this is a supervised problem, so we have labels for everything. And then there's 780 different ultrasound images. Cool. And here's some just examples of, of some of the different data that we're going to be feeding into our neural network model. And I'm not an expert in this, so I can't actually read these images and tell you more. Okay, cool. So the kind of starting point, if we don't assume any additional structure in our data, but we just want to learn a mapping from our images into our final classification label, a starting point could be to build a multi-layer perceptron. And we've already talked about MLPs and trained a few of them as well, right? Ish. Okay, and I know that Chethan yesterday just talked about the basic perceptron model, so I won't go into too much more detail there, but it's just to say that we have, this idea that you have a neuron, it's going to take different weighted inputs from all of the things that kind of precede that point within the neural network. So if this is, our hidden layer, we'll be able to learn these connection weights that feed into this neuron, and then we'll pass it through some nonlinearity as we were discussing earlier, and then that feeds forward to this given output node. So if we're just trying to do a binary classification, our final output could just be a single number or a single node, and its goal is to be able to give us the probability of being in class 0 or class 1. And then when we say multi-layer, just meaning we're stacking all of these layers of neurons and feeding it forward. So in this first part, which I want to make sure that we have more time to go into PyTorch, but here I just showed you how to train and specify an MLP just in sklearn. So scikit-learn is a very powerful and widely used toolbox within Python for all kinds of machine learning that's not deep. So a lot of if you're doing PCA and all these other linear analysis techniques, you can do those very easily in sklearn. And this is just a way of training a simple neural network also in that same framework. And so in order to specify our MLP classifier, we have a number of different, parameters or aspects of defining the architecture. So in order to specify this MLP classifier, we're going to need all these different things. So we need to specify the architecture, which is the number and the sizes of those hidden layers, right? So we know for the binary, we're going to have one node at the output. Our input is just the dimensionality of our data. So if we have like an 8x8 image, we'll vectorize those 64 different numbers within the image, and we just turn them into a vector of length 64, and then that's our input into our neural network. So basically for an 8x8 image that we vectorize, we would have 64 nodes at the input of our MLP, and then everything in between, the hidden layers are all fully specified by the designer. So the input will have a particular size output, and then we're going to add more layers or change the sizes of them. Okay, so that's one piece. And also, if I'm going too slow or you've already touched on a number of these things, please just feel free to tell me to speed up. And now we can it's also in the code too. Okay, so we have the architecture, which is the number of hidden layers and the size of each of them. We have our activation function, so that's just for all of the nodes in our network, what is the nonlinearity that's applied? It could be a ReLU, sigmoid, hyperbolic tangent. Also, we need to specify the optimizer. Have we talked about different types of optimizers? Not always. So I'm not going to go into a lot of details on all these things, but you're going to do some sort of gradient descent. You're going to do backpropagation as we've talked about, but then the way that you actually update the weights and your model is different depending on which optimizer you use. So SGD is kind of just like the most standard. Stands for stochastic gradient descent, meaning that we're going to take a subset of samples each time and backpropagate instead of using the full data set. So that's stochastic gradient descent. And then things like ATOM will help to accelerate more quickly by adding what's called a momentum term, which kind of makes it so that you can't go too far from where you were at the previous iteration. And sorry, I forget your name. Amit, yeah. And then, so ATOM is always best, so then we can just, not, not talk any further. Yeah. So going back to our discussion, it's like a lot of these things are problem dependent. And so a lot of this, for instance, I said we have a validation set, so you can use that validation set to maybe test and choose some of these different hyperparameters and using some kind of common knowledge to guide you to one of those to start. Okay, so we have our different optimizers. The other piece is, in practice, when we do this, we're going to have a limited amount of memory on our GPU. And so then that constrains the number of samples we can process. Especially when you have images that are large, it takes up a lot of memory. So one piece of this is, you're gonna process like a random or a chunk of your data at a time. And the number of samples you have is called your batch size. And it might seem like, oh, I'm just doing this for memory reasons, and this isn't an advantageous thing to do because you're getting a lot of randomness. But actually, a lot of theory now has shown that having finite batches of data actually imposes some additional regularization in your network. And so there's also kind of learning benefits that come from stochastic gradient descent and not processing all of your data at once. And then the last part is just the learning rate, which is going to tell you how fast you're going to descend on your objective. Okay, cool. And so then in sklearn, yes?
Can you say a little bit more about learning rate? Why wouldn't you want descend as fast?
Yeah, so we're gonna have some really cool visuals to go through some of these ideas later. So I feel like let's go through some of those, and then if you still have questions. But basically, if you have a really large learning rate, you could basically continuously overstep your minima. So you're kind of bouncing around from where you actually need to go to because your step size so large that you can never actually get into your true minimizer. So, and then slow learning rate just takes a very long time. Yes, did you?
Decide the size of the network?
So all of these are, or people joke that's like graduate student descent. In the sense that, it's kind of design parameters, and there are hyperparameters that you kind of have to adjust in order to maybe build the best network for a different type of data. But then for a lot of like vision problems, there's kind of well established, people have like built nice encoders. So for instance, the stuff I was showing with MYOW, where we have pictures of cats, we use a standardized encoder structure, and everyone uses the same thing. And then you're kind of just more thinking about how do all these other pieces come to play and how do they carry out, rather than the architecture design. But it is a whole field of study in itself, just to know how to appropriately choose an architecture. And in many cases, it's kind of done through some hyperparameter optimization. There are some kind of general principles. And so maybe we'll kind of talk a little bit about that, and then we could also talk offline. Okay, so this Mlp classifier and sklearn, we're just gonna pull in from sklearn this neural network package and then specify our MLP. And then we can actually write out the whole MLP in one line. So we have the Mlp classifier. Here's where you specify your architecture. So these are your hidden layer size. It automatically knows what dimension your inputs are and the dimension of the output based upon the loss. And so here you're just specifying everything that goes in between. So you'll notice that these are actually decreasing as we go closer and closer to this one-dimensional output. So that is a principle in the sense that, and we often will do things in powers of 2 just for nice, computational reasons. So it's like 512, 256, 64. There is this sort of idea that you don't want to compress too quickly. So like I wouldn't want to go from 512 to 1 dimension because you kind of want more depth so that you could learn more interesting nonlinearities. And maybe there's other things that practitioners want to see, or like, oh yeah. I want to know the magic number. So one thing that I was saying earlier is just this like thing of needing more than what you think you'll need in the end, because of, you need to give your network like more space to learn. So Mehdi, do you have, but starting with this principle of like less, and then seeing so this is a thing that you've taught me in deep learning, which is if you have a very deep and expressive neural network, you can completely overfit to your training data, meaning that you can actually get like 100% accuracy and nearly 0 error. So there is this tendency to actually add more so that you can start to overfit your training data, because then that tells you that you have enough capacity to potentially learn the true function of interest. And then you would, after you like make it overfit, then you start to regularize so that you can decrease the gap between your training and your test. So that's, I don't know, some principle. Yeah, especially for some of these like biology problems where you don't actually know if it's solvable and you don't know the architecture, you kind of do want to give yourself the ability to go really far and then come back, right?
Does that make sense? Right? What they're saying, like, if you don't know what you should expect, work it just to make sure you can learn and then go back. Does that concept make sense?
Okay, cool. So we've specified our hidden layer sizes and our activation. We have our ReLU. We're going to do the atom solver. We have our batch size, and then learning rate, and then just the number of iterations. So basically, after this, we specify our MLP. We're going to fit on our training labels and images, and then here we're just looking at the training and the test accuracy on those splits. So the first thing that we can see is our training accuracy is very high, right? So in this particular network, we are able to get to nearly 100% accuracy on our training. But then if we look at our tests, it's much lower than our training, right? So there's this large gap. It's called like our generalization gap, which tells us how far on test data we are from our original trained data. So this is something that we want to now decrease, right? We want to, like, probably our training accuracy will go down, but then our test accuracy should come up to meet it in an ideal case. Okay, cool. So I think this is a nice tool to be able to use pretty easily in Python through sklearn. You don't have to worry about too much. But it only gives you some capabilities, and it's sort of not as flexible as we would want for more general network design. So that's why we go to PyTorch or TensorFlow or some of these other toolkits that will allow us to build networks that are more complex, but like it's not going to be in one line of code. We're going to have to do a little more. So that's a trade-off. Okay, and so our MLP doesn't assume any structure on the inputs, but as we know with this particular problem, we have images, and so we have autocorrelations and real structure in the rows and the columns of the data. And so in order to build a model that can respect that structure, we'll move to a convolutional neural network. And I guess yesterday you would have seen convolution in time, right? Or this idea of like, in an RNN, you have this temporal property that tells you how to apply or how to process your inputs. And this is kind of a generalization to 2D now that we have images. And so here I'm just showing the idea of a convolution, but really it's just this idea that we're going to learn some filter, some kernel, and then we're going to basically, sorry, I'm just like looking at my picture. Here's the little kernel, right? And we're sweeping it along basically all of the pixels of our input image, and we multiply the center pixel with the surround from our filter, add all of those weighted inputs up to get an output, which is just the convolution of that pixel with our receptive field or with our filter. And then we do this over the whole image. So if we had like a low pass filter, right, everything would start looking more smoothed in space. And so what a convolutional neural network will do is it allows you to learn these filters that we're applying to images, but do it in this, flexible and sort of hierarchical manner so that at the beginning stages, you could learn really fine scale features of your input. And then as you go further and further, you can start to learn more conceptually kind of complex patterns.
Wait,
Yes?
so does it mean that your layer must be bigger than your input layer?
Does it mean that sorry, which layer?
I mean, the layer that you're feeding, so it looks like there are more, rectangle.
Oh, yeah, no, it's a good point. So there's different ways of dealing with padding, or the fact that my filter has some size and I want to put the center of it on every pixel of my image, but then when I'm at the edge, I'll have content that kind of spills over. And so typically you could either zero pad initially and let things spill over, or you can also specify something that doesn't go past the boundaries during the convolutions. Okay. I didn't know if there was something to add more particular about that, but we'll see. Yeah, we see a little of that pop up. Okay, cool. So now we're trying to solve the same problem that we did with the MLP, but now we're going to build a convolutional neural network, and we're going to do it in PyTorch. So again, we're just pulling in these different toolboxes or packages. Okay, cool. So now that we're in PyTorch, we're going to now build our neural network. But before that, we just have a few things that we need to do to like normalize the data and split it. And I'm not going to go into tons of detail, but we're going to come back to this idea. Data transforms, and then your transforms.compose. So the reason why we're going to come back to this is when I was talking about applying all those cool augmentations for SSL, that's done through these transform functions that you can define. And we'll see that in the worked example, and you could even play with different augmentations at the end if you want. But this is essentially like the way that you'll kind of create all the different things sorry, it's kind of, oh yeah, sorry. Okay, sorry, this is a lot. So I'm skipping ahead, but we'll show like, at the beginning, all I'm doing is normalizing. We'll go back there. But then there's also ways of creating augmentations of your training data. And it's not going to result in the same sorts of invariances that we described for self-supervised learning. But when we're using it with a supervised algorithm, it's basically going to create all of these other like possible inputs, and we give them all the same label. So that allows you to, if you have an image, you could rotate it a little bit, or you could add some noise, or you could do different things to it that will hopefully resemble more of what the data looks like at test time. And that should also help with your generalization. But so you can see here, I've defined this transforms.compose, and later on we'll have like more transformations. So this is randomly apply some random affine transformation that goes anywhere between 0 and 20 degrees. It'll interpolate, and then it also will rescale the image either by downsizing it to 0.9 or kind of upsampling it to 1.1 its original size. After that, we have like a Gaussian blur and a random horizontal flip, and then also some normalization procedure afterwards. So because all of these are randomly applied, as I said before, we have this composition of augmentations, but each step happens with some probability. So in the end, when you get an example, it could have a lot of different things applied to it, and it might look a little, different from what the original example is. So this is kind of a nice tool that's used both in supervised and also unsupervised learning. Okay, so let me go back. Okay, but here I haven't done anything too fancy. I didn't do any flips or filtering, but all we're doing for our transforms initially is just normalizing. And this is in order to get it so that it's z-scored data, we're applying that. And we notice that it's doing it to all of it. It's not a random apply. Cool. So we also need to define data loaders, and I won't go into much detail here, but just to say that when we're defining our train loader, it's a little different from the validation and test in just that we're going to drop off the final data that's like not in a batch. I don't have too much time to go through all this, but okay. So we have our training data, our validation, and our test. Cool. So now we're going to build our model now that we have our data loaders. And so this is just a picture of a kind of general convolutional neural network that has multiple layers. And we'll see there's a few other things that we'll have to think about in comparison to the MLP. But it has all of the same other components like batch size and learning rate and optimizers. Okay, so to specify our convolutional neural network, just as we saw before, we're going to have multiple layers. So each of this represents like different layers within the network. But now instead of having to specify something that's going to take all of the inputs jointly, we're going to have the ability to learn like a kernel or a filter that's smaller than our full size of our image, but it's just going to be applied, as I said before, in this like convolutional manner. And so in order to specify that, we're going to have to, basically for our layer, we want to give it 3 different inputs. We want padding, We'll have to specify the padding, which has to do with like the zero padding effect that I talked about when we kind of spill over the boundary. So that just says how many zeros do we pad around our image before we process it in that layer. Kernel is the size of the filter. So when I say 3 by 3 kernel, that means that we're going to take a little filter that's just 3 by 3, and we're going to learn its weights, right? So we can learn the structure we want, but we'll just have this like really small kernel that we're learning, and we'll translate it over the whole image. And then we can have many channels, which means instead of having one 3 by 3 filter, we actually have n channels 3 by 3 filters. So it's like you're learning many different possible features from the images. Okay, stride is, so I have this convolution, and if I move over 1 pixel at a time, each time I apply it, that's called a stride of 1. But if we say skip over a pixel each time we apply the filter, that would be, say, a stride of 2. So it's sort of telling you how much spatial downsampling you're going to do when applying the different learned features. Okay, so we have a convolution layer. Do you have a question? Okay, so we have a convolution layer, and then after the convolutional layer where we apply all of our filters of a particular size, we then will typically apply some sort of pooling operation after the convolution. And this pooling can be an average pooling or here a max pooling. But basically what it does is, you have this filtered output that comes from the different kernels. And then with the pooling, you're basically going to define like a window, and then you take the maximum value within that window. So it's a way of doing kind of like compression and downsampling, but it's in a learnable way. So yeah, if we do a max pooling with a kernel of 2 by 2, that means we'll put a little block down. So we'll have 4 pixels, and then we take the maximum, and then we have a stride of 2, meaning that we have a non-overlapping max pooling. So now we'll move over 2, do it again, and so on and so forth. So this really is a way of taking something that after being filtered is kind of high dimensional, and it's going to decrease it by a factor of 2.
So if you were averaging, would your strides be within the kernel?
So typically, you'll want to do non-overlapping max pooling. I'm sure there's some reasons to have overlap, but then you still do the average or the max or the min over that block, and you'd still do it non-overlapping. But it's just what operation are you using? Yeah. Okay, cool. So basically each of our convolutional layers are typically followed up by a max pooling. And so now if we have another layer, you can see like we started, if we have 32 filters, the output of this first stage of processing will be like 32 by 28 by 28, assuming that our image was 28. So it's like I've taken that image and I produced 32 different versions of it that are all filtered in a different way. And then we do the max pooling, and that's going to take us down to like a size of 14 by 14 instead of 28 by 28, but we still have the same number of filters. So we're not compressing across the filter axis. Cool, and so now in this next layer, we're kind of working on the same dimension of data, but now we've increased the number of filters, right, to 64. and then do another max pooling. And so what comes out of this you can kind of consider to be these features that you've learned from the visual inputs. So we'll just concatenate, like we turn those into a long vector, whatever dimension is at the output of our neural net, and then we plug that into an MLP. So when you have the convnet, you'll have all these nice convolutional structures, and then you do your final classification in the same way that we saw in the last example with the multi-layer perceptron. So before we went down to a single number because we had a binary classification, so we just had to go between 0 and 1. But if we do a more general like n-way classification, here this example from MNIST, so you'd have 10 different, you have 0 to 9 as your different classes. And so here we would do like, we would have 10, the output is actually 10 dimensions, so it's the number of classes. Did you guys talk about one-hot encoding, or might be too much? But yeah, so instead of it just being 1 and 0, the way you encode class 0 is by saying 1, 0, 0, 0, 0, 0, right? And the way you encode class 1 is 0, 1, all zeros. And so it's 10 dimensions, but you're encoding each of your classes through like a binary, what's called one-hot representation. Okay, cool. And so this is actually building our neural network in PyTorch. And so you can see it does require a bit more than with the previous example, but we also have more kind of capabilities. So here we've defined our model. It's sequential. The first convolutional is going to be, the first input is the number of input channels, number of output channels, so number of filters. Kernel size, so the 3 by 3, you just put in 3 if you want a 3 by 3, stride and padding. And so here's our first conv layer. So we're going to have, this is important. So because our image is grayscale, it just has a single channel for the input, because basically we just have the intensity from black to white being 1 as being encoded within just like a single matrix of values. But if you have a color image, you have 3 channels, right? You have R, G, and B. And so if you had like a color image that you wanted to process, your number of input channels here would be 3. But because we're dealing with grayscale, it's just 1. And then the next one is number of output channels. Kernel size is 3. So you can see the number of output channels being 4. Now this is the number that we're passing as the input to the next layer. And that's important. If you don't match the output dimensionality to the input of the next layer, you'll get an error. It's not just doing it automatically for you. So then 4, 8, 3, we pass through a ReLU. So this is just calling the activation function here. And then after this, we're passing it through this max pooling layer. So you can see that all of these different like architectural components are one-liners within PyTorch. Like you can fully specify this whole layer using each of these building blocks. So we have a conv 2D layer. There's also conv 1D if you're just doing a temporal convolution. And then max pool 2D is just its own. And then it knows I'm going to define my kernel size as 2, and it automatically enforces a stride of 2 as well. Cool. So this is sort of, showing how we can build a multi-layer convnet. And then as I showed, this last part is going to flatten everything that's coming out of the convolutional layers. And then we're passing it through a linear layer that just goes down to 128 dimensions. And then finally, the output for our binary classification goes from 128 to 1.
So after this, what you're on the top, I have a question for you guys on your top layer where you see it's like 1, 2, 1, 4, 3. Can someone tell me why you have 1 input channel and 4 output channels? Why are there 4 output channels? Like, what is it? Why is it 4?
I actually don't know the answer to your question, so.
Okay, great. I'll let Betty answer in a little bit, but I know at least two of you in the audience know the answer, so. All right, does students want to explain? No? All right, Betty, do you want to explain?
So the question was why you have one filter there and four out there.
Yeah.
So the four represents the number of kernels I'm going to choose to do the convolution process. So typically, each pixel initially input there is represented by the intensity level, like 0 to 1. Each of those kernels are going to after the convolution is going to contain one feature, and at the end going to have four features describing each pixel in the
And then, so what Betty said is like, you have one channel in, and then you have four out. And so when Eva showed you that image of like that 3x3 thing sliding over the image, that's your kernel. And so what Betty's saying is you have four of those. You don't just have one that you're learning with three, you have four of them in her birthday. So this box that's sliding over the image, you actually have four of them.
Right.
And each four of them are what mentioned.
Yeah, so that's the number of channels, the number of filters that are being applied. I was confused because I thought like it was supposed to be 4 for some reason. I was like, I don't know, that's just the number of channels that we chose, right? Or the number of filters.
So that means that you don't just necessarily have one filter for every layer. You can have as many filters for any layer as you want. And all of those filters are learned. And they're not going to be learned to be the same thing.
So you imagine like each filter is looking for a specific pattern. And like that's why you have multiple times. So if you have multiple patterns looking for an image, you're going to have different types of filters maybe that are looking for.
Does it make sense?
But just for clarification, so the difference is just like different kernels for different channels, and how is like the parameters of the like kernel different? Is it like just randomly defined?
Oh, yeah.
And also, why is 4 different kernels instead of like, for example, 32?
Well, that's the question I thought you were asking. I was like, why was it 4? And there's no reason in particular. Like you could set it to 30 or 100. There's probably some principle of like scaling up the number of filters.
Slowly increase the number of filters, because if you start with a very huge number of filters, this means that you're going to have a lot of computation. Initially, when the image is like full spatial dimension, you start doing the downsampling, it's going to be too expensive. So usually,
I see,
as
yeah.
you go down to the side, like spatial side of the image, that's when you start scaling up your number of kernels that you're using for the convolution. Because it will be, as you go smaller, that's less expensive, and
Yeah, it's a good point. And then to your question of like, how are they set, or, how do you figure out the different kernels? So that's what those are part of your weights, right? Or the model specification that you're learning through the gradient descent. So for a given 3x3 filter, right, you're going to have 9 different values. And basically you're gonna fit your model to figure out what all of those different kernels or filters look like through learning. And then, this point about like how many filters you have as you go further. The key thing also is, right, so as Mitty was saying, the filters at this stage are working directly kind of on the raw pixel intensities. And so that's going to be able to pull out kind of more fine scale features. But as you notice, like these filters that are learned are then being processed by a secondary layer that's still also using like some fixed kernel size. So what happens as you go further and further, you're going to see more and more kind of global features of your whole input that are going to be learned through kind of later layers. Whereas at the beginning, it could be much more fine scale, like, oh, this is a low pass filter or an edge enhancer or something to that extent. Yes.
So is it good to think about each kernel or each filter as like a feature? Like, is that like an analogous?
Yeah, I mean, in the sense that it will produce a feature map, right? So if I take an input and I pass it through that kernel, if it is a low pass filter, meaning like almost all the values are kind of equal, so you're taking more of an averaging operation, then the output after I feed through that will be the same image, but it's going to be that filtered and like downsampled version. So in that sense, you do have features of your image, but they're also still spatially configured. Because it'll look, I mean, at the early stages, it really will look like the same input, just through some different transformations. But yeah, as you look at some of the ones that happen further in, it's just, you know, what's actually going on in there is harder to see.
Another question.
Yeah.
After the first convolution 2D layer, there's another one, like starting from 4 channels to 8 channels. Does that mean every channel, every tutor has an additional 2 tutor for each of the tutors after the first layer?
So it's kind of, yeah, so it's not that it like keeps on expanding so that you'd have a multiplication of all those things. But the output after the second one will actually be 8 different outputs. But then it's, I forget. So it's like in the previous one, you're actually doing the compression across all of the channels simultaneously.
So the kernel, like just you stack your now 4 channels, right?
Yeah.
Your filter is going to like have not only 9 waves, but have 9 multiple vectors.
Okay.
Like doing the
Like a cube.
multiplication and then computing a single channel. So you have like 8 different 3 by 3 by 4 kernels that will be circles.
Okay. Yeah.
Why is that very different? Why is that big channel?
That's all again arbitrary.
Yeah, it was just because it was just the specification of the number of filters there. Awesome. Yeah, these are great questions. And yeah. Uh-huh.
So there were 2 layers and then next point and then there's 1 and then next point.
Yeah, so I think, well, as Mehdi was describing with this first one, because we didn't have a max pooling, it just stays at the same dimension that it was previously. And so, you know, you could think about this as kind of processing things at the same dimensionality and learning a small number of like 4 filters of the inputs. And then once we go to the next layer, then we start downsampling. So you don't have to apply max pooling. It's just that as you're building more complex, like multi-layered networks, you want to kind of have compression. And it also will encourage the network to start looking at more global features because it doesn't have that same resolution as well. But yeah, a lot of this stuff is kind of by different hyperparameter optimization or just, you know, knowing the problems. Yeah. Oh yeah, please, as many.
So in the beginning, this image has say 3 channels, and I still want 4 kernels applied to each of the channels. So should I enter like 4 in this second input or 12?
So at this first stage, actually sometimes I forget how all this works, but I know that at the first stage where you have the 3 channels, the filters are applied separately on each channel. And so you would still have 4 filters that you're learning. But like they would be applied in the same way to each channel. And then you can also, as you go further in, you can actually compress all of those layers into like a single feature map. But let's hear the expert.
No, in that case, just change the 1 to a 3. That's number of channels. And from the start, the kernel will be like 3 by 3 by 3. And then you can scale the 4 to 12, but I wouldn't say that's like necessary.
Right, and then yeah, that piece of like passing in the 3 here as well is important, yeah.
But obviously, if you have 3 channels at the beginning, that means that you have more complexity, like there's more factors in that possibly, and it would make sense to go from a 4 to an 8 or 16.
Okay, cool. And then if you actually did want to do convolutions in 3D, like it's not just that you want to process the channels independently. If you have 3-dimensional like microscopy data, there are other like convolutions in 3D that can be specified where you're actually not just sweeping it in 2D, but you're actually moving your 3-dimensional kernel throughout the whole volume. Okay. Cool, so that sets up our neural network. Once you have it specified, if you use this just like print model, this is nice as like a good way to share your architecture with other people because it's a very standard and it has all the feature or all the hyperparameters. Okay, cool. So I won't have time to go into like different choices of different losses. But what we'll use here just for our binary problem is the binary cross entropy loss. But if you go into PyTorch or if you just search the documentation, you'll see tons of different loss functions that are kind of already built into PyTorch. So you could use a mean squared error, or you could use an L1, or some of these other classification-based losses. So here we're just specifying what it is. We'll also need to define our optimizer here. So in this case, we can, when we're defining our optimizer, we'll both say what type of solver, and then we can also specify our learning rate at the same time. I feel like I'm going, or I don't, how much time do we have?
5 minutes, but I feel like it's productive.
Oh, we have 5 minutes left? Okay. Okay, cool. So I'll try to go through some of these examples a little more quickly, and then you'll have the opportunity to play with this at a different time. This is just the main kind of pieces that we need to specify to actually train the neural network. This is very standard, and you'll be able to find a lot of examples that use this same structure. So we're going to have a forward pass, where we're going to, define our inputs and targets. We're just zeroing out the gradients, defining the loss, and then this loss that backward is doing a backward pass, so back propagating the gradients, calling our optimizer, and then this is just logging as well. Okay, so this gives us the main kind of optimization loop for training, and then we have a different one for test, because obviously we're not going to back propagate our gradients and we're not learning. We're just going to feed the examples through in a forward pass to get the outputs. Okay, so this is our test. And here are just some additional plotting utilities. Cool. Okay, so now what we'll do are just kind of step through a few different outputs that are generated for different choices of these hyperparameters. So in this first case, I'm just looking at, okay, so here with whatever we've already baked in, we have an architecture, we have our loss function, etc. This is just what the performance of this network looks like. And what I'm showing here is overtraining, so over epochs. Did we talk about what an epoch is versus, okay. But so we have a full data set and we specify the batch size. So that's going to tell us how many examples will go in the first batch and the second and the third. And then when we go through all of our batches, so we've done a full pass through all of the examples in our data set, that will be considered an epoch. Okay, so here we're going across training. We specified 200 epochs, and then we're plotting the training loss and then the validation loss curve, right? And so what we can see is, well, in terms of accuracy, and this is actually the loss that we're trying to minimize, so you kind of get different pictures from both. But we can see a very similar effect as what we saw with our MLP, where we actually have a really large gap in accuracy between our training and our validation. But it is higher than before, right? Like we got a 70% on our test with the MLP, and now we're actually, doing reasonably well in terms of overall accuracy. And we can see similarly, like we want to see that our loss, which is what we're trying to optimize, is decreasing throughout training. So this is showing us that we're, getting decrease in the loss. But if we look at the loss on the other hand for our validation curves, right, we're seeing that the loss is actually kind of blowing up very quickly at the beginning of training. Okay, cool. And then we can just kind of zoom in on this as well. Our validation and our tests are actually getting very similar, but there's still a large gap with training. Okay, cool. So this is just an example so we can look at either having a really high or a small learning rate, and what does that look like in terms of your loss landscapes and all that. So, so in this case, we're trying to start initially with a very small learning rate. So we've set it to 1e to the minus 4. And so the idea is that, on your training, what you're seeing is decrease, but you're going too slowly to actually see that full convergence that we saw before. So if we fix the number of epochs but have a lower learning rate, we're only going to get so far in our training. And we can see this very clearly that like this actually hasn't bottomed out, or it hasn't really gotten to a very low amount of loss. So this kind of gives you some insight if you see something like this, that you probably should increase your learning rate. Or if you want to go very slow and you have a lot of compute time, you could increase the number of epochs, and that will still get you there eventually, but very slowly. And here we're using atoms. So we're using momentum, but it still hasn't given us enough because of the learning rate. And then we can also kind of similarly track what the accuracy looks like there. So on the other hand, if we instead use a very high learning rate, so now we're setting this to a really large number, 10, we can see a very different picture. So mainly what's happening, you're not seeing that, nice steady decrease. And often when you have too high of a learning rate, basically your loss is going to be jumping around and fluctuating kind of wildly, because as I said before, you're kind of overstepping and you're going too far and you're missing your... I guess alternatively, like in the validation curve, you can definitely see that flipping happening very clearly. Okay, cool. So did that help to answer your earlier question about learning rates? Okay, cool. But I do think that being able to look at this when you're training your own neural network and kind of get insights into it is really helpful. Now, just some examples going through the influence of the batch size. So as I said before, you want to have, well, maybe the memory is a constraint on your batch size. So you have to have a small enough batch size to fit it into memory. But when you have too small of a batch size, you're also kind of seeing very different examples across each training step. And so like if there's variance in that, like the gradients could actually be kind of pushing you in different directions. And you don't really have enough information to train the network effectively. So this is an example where we have a very small batch size. This is over a very small number of epochs. Is there something to like note about knowing that so it's kind of weird because your batch size and your learning rate and all these things are kind of interacting in an interesting way, but do you have anything else to say about batch size? Yeah, so there's kind of like a trade-off. I mean, the larger the batch, it shouldn't be a bad thing, right? Except for just that stochasticity that I was talking about earlier, that kind of helps you a little bit.
But also when you have smaller batch size, since probably less confident in the steps that you're taking and should go slower than if you have more samples to prevent.
Yeah, that makes sense. And then this is, like here we're looking across epochs. So as Mehdi was saying, it's like you have small batches, which means it takes a lot of steps before you get to a full epoch. But if you were just to look at the loss as a function of the actual steps across those batches, it's, you know, this really crazy business. Okay, so 5 minutes? Sorry, I went over on my first lecture and now my second one too. Okay, so in this next section, I won't have time to go through in tons of detail, but it's really useful for your own just looking back later. So we have a few different tools for regularizing. So we talked about this huge gap between train and test. And so how do we now make a model that should perform as well on the test as the train? And we do that through different forms of regularization. The first one is, it might not seem like regularization, but it's often used, and it's just called early stopping, meaning that just because I specify like a certain amount of time that my model will take, doesn't mean that that's the best point to stop the model. So what you can do is you can use a validation set and figure out an earlier epoch to stop the model at where you get good validation performance. And so what does that look like? So, right, so early stopping, it relies on like a held out set. You're gonna just evaluate the validation accuracy and basically pick the point that has really good validation accuracy, and then you use that model for your final test. So it doesn't actually really, like in this case, the early stopping doesn't really help us, but you have tools to use it in other cases. It can be more useful. But I think we actually decreased our overall validation performance through doing this somehow. So, you know, we were at 85%. And, oh, okay, sorry, this was before. So our training was 93 and our test was 83. And then after early stopping, we have a very small gap, but also our training accuracy went a lot down, right? Because we didn't get it at its best point on the training. We went back a little bit in time. Yep. Mm-hmm. Right. So here, yeah, it would be somewhere around here.
So we probably, if you guys have to go down and see how early stopping epoch, and you just got like early stopping epoch, and you go into print early stopping epoch, probably see exactly where, and my bet would be that it lines up going to validation.
It's an epoch 40.
40.
But I think also there are two ways of like doing early stopping, either from the loss, when the loss is minimal, or from the accuracy as well.
I think we did the accuracy. Okay, got it. Okay, cool. Just, you know, we have our accuracy curve over here versus our loss. And so, yeah, we could take the minimum of either of those. Okay, so the next class of regularization is weight decay. So basically it's just applying like a norm, like an L2 norm or an L1 norm on your weights. So it's basically just saying, okay, I'm gonna learn all these weights, but I don't want them to grow too quickly. And so I'm gonna reduce their size with just some kind of standard explicit regularizer. And I guess you guys probably went through ridge regression. So that's just using like an L2 norm, and that's a very common way. And actually, you see, it's so common that it just is embedded within our optimizer. We can just say that we want weight decay. So it just helps so that the weights don't grow that large. And then the third class, which I would say is probably more widely, or it's very widely used and can be very powerful, is to use network dropout. So before I was talking about dropping out the activity of neurons, and that was dropout in our input. But another thing we can do is actually drop out neurons within our network, within a layer, with some random probability. And what that does is it makes sure that we don't overfit too hard to like one node carrying all the information, because at different training instances, we have to still be able to decode from different neurons if we've dropped that important one out. So this would just be like a standard MLP. And then the idea is you're randomly selecting some probability of nodes to drop out. And this is used during training to improve generalization.
Does this affect the distribution of kind of the representation if you're forcing particular neurons to drop out? Does it force it to be more widespread?
Yeah, so it's a good point. Like people kind of have thought about this, yeah, in that context where you're kind of, as my example was like, maybe just early on in learning, you have like one path through your neural network that's really effective. So you just keep on strengthening that, but you're not using everything else. And so it kind of encourages you to not get trapped in that. And so people have also modeled it as sort of like, there are these things called random forest, or there's other classifier where you actually have many models that you've learned, and then they're all kind of like pooled together. And so people have talked about network dropout as kind of embedding this property where you could actually have ensembles of models that are kind of being learned by your network. Okay, cool. So now, like, okay, great. So now we're going to embed this, here we are. So we can't exactly do dropout very easily, like in convolutional layers, because like a node means something different. So we'll typically apply dropout into our MLP layers or our linear layers. And here we're just specifying the probability of any node dropping out. So it's like 50%. You could play around with that dropout rate. Okay, cool. So finally, we start to, actually this is kind of similar, but with dropout, we're starting to be able to like close that gap even further, but then still maintain a high accuracy in our training set in comparison to the early stopping where we were losing a lot on the train to get a smaller gap. Cool. Great. And then just in this final piece, I've already kind of given a little bit of a hint of it. This is just how to now use different augmentations of your data to help further improve generalization. So what we'll do is we apply these different like spatial transformations or flip it or rotate and then renormalize. And so now when we're training, each time that our data loader gets a sample, it's going to apply all these transformations. And then we'll get like more varied data that we're training with. And these are just some pictures of some of what the augmentations look like when we're like rotating and rescaling. And then finally, in the end, we can analyze what the performance of our algorithm is after we apply different augmentations and dropout and early stopping, and start to close this gap even further. So that's the end of this notebook. I hope that these will be useful tools, both in dissecting a neural network and then just kind of all these general classes of regularization. Cool. All right. Thank you.